Hello everyone, welcome back to the channel. My name is Danny, and today I wanted to talk about asynchronous programming in Rust. Before we get right into the code, I want to give you a quick overview and an analysis and breakdown of concepts and vocabulary so that you understand what a thread is. What does that mean when I say task, cores, CPU, concurrency, parallel, asynchronous? How does this all tie together, right? First thing first, a thread. What is a thread? A thread is pretty much a process, right? It's a program running on your computer. And it's usually synonymous with core, meaning if your CPU has 4 cores, for example, then that's only 4 threads that can be ran at the same time. Of course, you can spawn as many threads as you like in your program, but there is a limitation. If there's only 4 cores, then only 4 of those threads can be ran, and the operating system will be responsible for managing the rest of the thread to see which one gets switched on and off so that everybody gets a turn to run. So that's threads. Now, a task, if you break it down even further, is what runs inside of a thread. As you can see with this particular example, this thread has 2 tasks, right? And they're spawned at the exact same time, and that's fine. Now this thread, for example, has 5 tasks and they're spawned at different times and they might be ran at different times. Task runs inside of a thread, and usually a task is managed by you, the programmer, right? The Rust programmer, by using asynchronous programming. A thread is managed by the operating system for the most part. So now we go to concurrency. So what does that mean? Concurrency actually could mean either asynchronous or parallel. So it's an envelope term, right? So something that runs concurrently could mean that it's running asynchronously or in parallel. It can be either or. Now, if you take a look, asynchronous programming is basically this. If you can see, this thread has 2 tasks inside of them, and the programmer is managing, or rather the Tokyo runtime, or whichever runtime you choose inside of your Rust program, is managing how these tasks are being ran and at what time and basically at what duration, right? So as you can see, it kind of pass on, pass off, back and forth. It's almost like one person multitasking between different chores, right? Whereas parallel is basically 2 tasks being ran at the same exact time. Now with this is like me spawning a twin version of myself, and then we both tackle the chores together. However many chores I have, most likely I'm going to be done twice as fast. Now on the other hand, asynchronous, I'm not going to get the task done twice as fast, or I would not have any performance boost at all if you really think about it, because it's still just me doing all the work. I'm just jumping back and forth and allowing each task to occupy my time evenly, rather than just running through one and then running through the other sequentially. A great example of this would be, let's say if we have 3 clients trying to query and fetch our server and then get a response back accordingly, right? So in a normal program or a normal logic, you would think first come first serve, right? That's fair. 3 clients, yellow, red, and blue, they all go into the queue, right? If yellow came first, he's gonna be the first one to get a response, right? And then red will wait, and once yellow's done getting his response, he'll get his response, and then blue finally is gonna have to wait until both of these guys are done before he can get his response. But if you think about it like that, that's not exactly good user experience, right? You don't want to make the last guy wait that long for just to get a response back from a server, because in a real web server, for example, there's hundreds of thousands of requests per second, and just because you're the last guy to hit the website, it shouldn't be so that unpleasant for you to wait and sit there and have that much latency and lag time before you can even get a response back. So basically, this is where asynchronous programming really shines. So instead of making making red wait for yellow and blue wait for red, we're gonna go ahead and send a response back to yellow, and then we're gonna switch off and send a response to red, and we're gonna switch off and send a response to blue. Now this, even though, like I said, this doesn't magically make it so that our server is serving these requests, these response back, they're not 3 times faster. They're not. Matter of fact, it's gonna take 3 times as long for yellow to get his full response, the entire packet, this way, than if we did it the other way right here, right? However, the advantage of this is that everybody gets a little bit of something all the time, so that blue does not feel like he's being left out and he has to wait in queue for 100 or 1,000 of other clients in front of him before he can even get a single a single response back. So this is kind of like in a restaurant, right? Like if you ever work in a restaurant as a server, if you get, let's say, triple sat, right? You have 3 tables sat down at the same time. Now you could go to the first table and just basically take the order, go punch in the order, get the food, serve it to them, and then once they're done, you go to the next table and then you start over. You get the order and then you go, you get the chef to cook the food, you bring it out to them and give them the check, they pay, they leave. Now you go to the third table. I mean, that's extremely inefficient. So what would you rather do instead is probably go to the first table and say, hello, my name is so-and-so, I'm here to serve you, but give me 1 second, I'll be right back. Then you go to the red table and you say, hello, my name is so-and-so, I apologize for the wait time and how busy we are, but I will be right back. Just to let you know, I do acknowledge that you just sat down and I will be right with you. And then you go to blue and you do the same thing. And then you go back to yellow, now you take their food order. You go to red, you take their food order. Go to blue, you take their food order. So basically that's asynchronous programming. And as you can see, it doesn't magically make it to where each table is somehow it's going to finish their meal faster or get their food, their service faster, but it just makes it so that everybody gets a little bit of something at all times so that they don't feel neglected and they don't feel left out. So that's pretty much it, and I think it's time we go into the code and understand how that works. Alright guys, so let's get right into it. We're going to start with our very first example on asynchronous code, and shout out to Green Tea Coding. Man, I think he's one of the best, if not the best channel to learn Rust. And this is very much inspired by him, and I'm going to start with his example, and we're going to work our way up into a more complex and a little bit slightly more complicated operation in a little bit. Okay, so let's get started here. So we're going to start with a function. So every asynchronous function has to start with async in front of the function name, and we're going to say async function and name the status, get status function, and we're going to take in a URL as a string slice. So what we're going to do is we're going to try to, as a very simple example, we're going to try to fetch 2 different URLs from 2 different websites and see how long it takes for each one of those websites to return a response status code to us, right? So we're going to return a result of either a status code. I already have everything imported just to save time, by the way, or it's going to be a dynamic. It's going to be a box wrapped in an object trait. A trait object wrapped in the box, and it's going to be a dynamic implementation of std error, right? So just like that. Okay, so now we're going to say let the status equal request, if I can spell that, request get, and we're going to pass in that URL, and we're going to make sure to await it, because as you can see right now, it tells us exactly what's being returned here. It's going to be a future that's being returned, and a future always has to be awaited, otherwise it doesn't do anything. An asynchronous function, if you don't await it, it's just not going to do anything, because it needs to be awaited in order for the future to be polled, P-O-L-L-E-D, so that it can be polled into being driven to completion. So that's a more conceptual explanation that I'm going to get into later on. But for now, let's say await, and we're going to bubble up any error. If we catch any error, if there's no error, then we're going to go ahead and get the status, and we'll return that as a status code. So as you can see, the status is now returning the correct type, so we can keep going. But first of all, before all that, we're going to say let's start time equal instant now, so that we can get the timer started, and then let duration equal start time dot elapsed dot as milliseconds. Okay, and then we're just gonna print out the result. So it's gonna say it took however long in millisecond ms to fetch that URL. So duration and URL, there you go, and we're going to return an OK status with the status code inside. Right? Is that okay? That should be okay. All right, so now let's get right into the main function. We're gonna start with two different URLs, but actually we're gonna also get a timer going here too in the main function, and we're gonna start with two URL. It's gonna be URL 1. It's gonna be a random URL as a string slice. Let's just say http s www.google.com. That's the first one, and then let URL 2 equals YouTube. Okay, so then we got two URLs, and we're gonna go ahead and fetch the status for each one of those URLs, and we're gonna see which one is faster, right? So since the get status function is asynchronous, we're gonna go ahead and await it, right? Because well, actually, let me show you guys something. So let's say we do let stat1 equals get status URL 1, right? And then let stat2 equals get status URL 2. So if we run this code now, it should print out however long it takes for it to fetch the website from the server, right? Because yeah, right? So let's try that, okay? Let's try that. Let's see what happens. Ignore all that. So as you can see, nothing happened. Like I said, the reason being is because an asynchronous function only returns a future. It doesn't do anything else. So if you don't call await on it, it's not gonna execute. Like all of this is not gonna execute. All it does is basically wrap up all of these. So when you call an asynchronous function, if you just call get status, all it does is wrap all of these up into a future, and it's gonna return that. So unless you call await on it, it's not even gonna run any of these codes at all. So we're gonna do that by calling await. Right? So now we know it's gonna actually execute, right? I know we gotta unwrap it, but I'll unwrap it later. Let's say print line, and we'll just print out the status code here. It's gonna be stat1.unwrap. Oops. Okay, and then stat2.unwrap. Okay. And let's see how long it took for us to finish that entire operation in the main function. So start time dot elapsed dot as millis. Overall execution took however long in milliseconds. Okay, now let's see what happens when we do this. Okay, let's go ahead and run this code and see what happens. Oh, hold on. Only allowed inside function to await. Oh, okay. Well, yeah, I forgot to mention. So you cannot call an await on an asynchronous function without it being inside of an asynchronous function as well. So you only can call await inside of an asynchronous function. So I need to do that to main, correct? But if I do that to main, it'll give me an error also because main is not allowed to be an asynchronous function. So therefore I need to have another trick, which I use Tokyo for, which is gonna add an attribute here, and it's gonna be Tokyo main, right? And that's what it's gonna do is it's automatically gonna wrap the entire main function inside of a synchronous function. So it's gonna unwrap everything to be just a normal function of main, and inside of that main function, all of this is gonna be an asynchronous function, if that makes sense. Okay, so now that our code is gonna work, we can go ahead and call it. Oops, oh crap. Let's see, call go run Q. Okay, so as you can see, it took 176 milliseconds to fetch Google, and it took 374 seconds to fetch YouTube. That makes sense because, you know, Google is just one single page with nothing on it, just a search engine, whereas YouTube has to load up everything else and all the videos and all the recommended videos and all that onto the main page. So that makes sense why it took longer. And if you can see here, this is the key right here. The overall execution took 551 milliseconds. So as you can see, it didn't really do anything asynchronous at all. It took 176 and 374, so the combined time was 551. I mean, that's not good, right? So basically, it finished looking for this, and then it went to YouTube. So there was no asynchronous at all. There was no jumping back and forth. There was no concurrency. It was just one task after the other. So what was the point of that? What was the point of even calling it as await, as async? I mean, if you would have done this normally, it would be the same result. You know, if you would have just left it the same as a normal function, it'd be the same exact result. So what are we doing wrong? Well, the thing is, whenever you are calling an async function, the way that you're calling it right here, it doesn't have a runtime. So a runtime is basically like the orchestrator, right? It's like the main boss, right? It basically oversees all of the asynchronous functions, so that it knows, it's the manager, right? It knows when to stop executing one code and check on another code, and just keeps going back and forth. It knows when to poll which future. Right now, you're calling two asynchronous function, but without having an orchestrator, without having a leader, basically a runtime, it doesn't know what's next. So you're calling stat1, you're calling get status 1, so it goes here, and then it's supposed to await here, meaning it's supposed to give back control to the runtime to say, okay, hey, look, I'm gonna go look for this status request real quick. You can do whatever you want. But who is it giving back control to? It doesn't have anybody. So it doesn't even know that there is another function down here that needs to be ran. It doesn't know that. So during the first call of get status, even though you tell it to give up control and say, hey, since you're busy, give up control so that someone else can do the work. It doesn't know that there is another get status function down here. It doesn't know that. So it's like, okay, well, I guess I'll keep going. And it finally finish, and then it goes to the next function, and that's what happens. And so the way for you to be able to call a runtime is to use Tokyo, right? Tokyo is a very popular runtime in Rust, probably the most popular right now. So we're gonna say this instead. We're gonna say Tokyo, and it's gonna be a join. Right? So join is a macro that allows us to call an arbitrary number of asynchronous function. Basically, it allows us to pass in an arbitrary number of futures, right? So you can pass in as many futures as you want. So I'm gonna say, so first of all, I'm gonna go ahead and comment this out, okay? And I'm gonna say join. Let's do the first future, get status URL 1. And by the way, you don't need to call await on the function inside of join, because join knows to await it, because it knows that these are just futures. It needs to be awaited, right? So get status 2 for URL 2. Okay, so you're saying, hey, Tokyo, create a runtime for me, right? And then here's 2 tasks for you to manage. So Tokyo, go ahead and manage it however you see fit. Right? Jump back and forth, use your concurrency, whatever. So in order for that to happen, it's gonna return a tuple of let's see, let's do stat1 and stat2. Okay. So now you should see something a lot different than this, right? It's gonna take the same amount of time to fetch. However, it's gonna be the overall execution time is gonna be a lot faster. So let's see. Okay, so as you can see, what happens here? So this time it took a little bit longer to fetch YouTube, and as you know, I mean, each time is gonna be a different number. So 178 to get Google, 413 to get YouTube. However, the overall execution took 418. So it basically took the same amount of time as it was just to get 1. So it's a lot better than the first one, right? The first one, it took a combined number to get 551. This time it only takes whichever is the longer number. I mean, obviously it can't be this one. It can't, because then how is it gonna be able to fetch YouTube? So however long it took to fetch YouTube, so that tells you that Google was able to start fetching and then give up control so that YouTube can be fetched. And however long it took for YouTube to get fetched, that's pretty much however long the entire operation took. So that was a huge improvement, right? So another way that we can test this out is to say, how about we do another one, right? I'm gonna add another function here that's gonna be basically in the background the entire time. So let's call it heartbeat, right? Because it's like a heart beating. And we're gonna pass in a count, okay? And the count's gonna be a U32, it doesn't matter, okay? And we're gonna loop through it. It's gonna loop in perpetuity, right? It's gonna loop continuously. Let's do a sleep. So it's gonna be a Tokyo time sleep. This has to be a sleep in Tokyo time, by the way, not a sleep by the STD thread, because if you sleep in the thread, it's gonna sleep the entire thread. And so nothing is gonna work while it's sleeping. This is a sleep call from the Tokyo module, meaning it's gonna sleep that task. So it's sleeping on an individual level rather than the entire thread being slept. So this sleep is gonna take in a duration from, we're gonna do micro, so we're gonna say every 25 microseconds it's gonna sleep. Okay, yeah. But we're gonna do a beat first. Beating, right? And then we're gonna keep increasing the count by 1. Let's see, I forgot an exclamation mark. Okay, so now, oh, has to be mutable. Okay, so now let's say if we call the heartbeat function right before we started calling the statuses, right? We call it status get status. Let's do this here. We're gonna go down and let's call it right here. Okay, so what happens if we call the heartbeat function here? We're just passing a 0 for now and a wait. So what happens? What do you think is gonna happen here? Well, I can predict that it's just gonna keep beating and it's never gonna get here, right? Because once again, Tokyo doesn't know that this function exists. So even though you call it as an asynchronous function, oh, by the way, you gotta await this, because otherwise it's yeah. So this is the point where heartbeat is supposed to give up its control to the Tokyo runtime, but Tokyo doesn't know the heartbeat even exists. So as you can see, it's just gonna beat, 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 beat. Yep. So as you can see, it doesn't even know that heartbeat is part of the asynchronous function at all. So it doesn't get to relinquish control to the Tokyo runtime. So what you need to do is instead call it like this. So we can call it as Tokyo spawn heartbeat 0. So spawn is just gonna spawn a new task for the asynchronous function. So now Tokyo knows, oh, okay, so here's the third asynchronous function. So now that it knows, so that whenever heartbeat is giving up control, the Tokyo runtime knows to go ahead and get started on these two next asynchronous function, right? So, and spawn also has a unique feature in that it guaranteed that spawn will start right away. You don't even need to call it it's gonna return a join handle, but you don't need to call it. But what it does do is not going to guarantee that it would execute to completion, which is great for us because we don't want heartbeat to keep executing. We want it to stop as soon as the fetch functions are done. So as soon as these two are done, we want it to stop. We don't want it to keep going. I mean, because if not, it's just going to loop forever. So let's see how that works now. Perfect. So as you can see, it beats. And then it gave up control here to fetch Google, right? And then it kept beating. It gave up control here to fetch YouTube. So the overall execution still only took 520 milliseconds, which is the same amount of time as it took to find YouTube. So even though it has an extra function now there's 3 asynchronous function being ran with Tokyo, it still only took 520 milliseconds, right? Of course, since heartbeat is returning a join handle, I mean, if you really wanted to, you could do it like this. You could say heart equal the join handle. So heart is going to be the join handle, and what you could do after is to join that join handle. So you're going to say heart dot await dot I think it's join, right? Unwrap. You're just going to unwrap it. Okay, so when you call it like this, when you await a join handle, it's gonna make sure that it blocks everything until it's finished, right? It's gonna block the entire thread until this task is finished. So now what you're gonna see is the heart's gonna start beating. You're gonna fetch the two websites. Everything is gonna be done. However, the heart's gonna keep beating, so it's gonna keep beating forever, which is not what we want, but that's what's gonna happen, just to demonstrate what it means when you get a join handle return from a Tokyo spawn, and then you call await on it, right? So now it's gonna make sure that the asynchronous function heartbeat is gonna beat until completion. So let's see. Yep, there you go. As you can see, it kept beating until I finally canceled it. It kept beating even after it found YouTube. Where? Right here. It found Google, it found YouTube. It took 436 milliseconds to find Google and YouTube, which is great, but then it kept beating afterwards, right? Because we call await on it, on that join handle. So that's not what we want. We actually only want it to beat until the two main functions are finished. So we're gonna go ahead and delete that, and let's run that again. Man, I'm sorry for the lag. Everything is just so slow whenever I'm recording. Come on, what's going on? So there it is, guys. So as you can see, it beats, the heart beats, and then it found Google, and then it found YouTube, and then it just shuts down, right? So that's how we do asynchronous function in this way, making sure that we have a Tokyo runtime to manage every single asynchronous function that we give to it. So the Tokyo runtime is a very important component of this type of operation. And as you can see, you can adjust it however you like. And then there's another way that we can also do this as well, which is called select. So select, instead of joining it, we're gonna race to see which one gets finished first. So we're gonna do so let's go ahead and comment this out first. So now we're gonna do select, and it's gonna be a macro the same way. However, it's gonna be slightly different, because instead of returning everything as a tuple, we're gonna have a return value for each one of the two function. So it's gonna be stat equals get status of URL1, right? And if that one succeeds first, then we're gonna say print line, we're gonna do stat, we're gonna print out the stat, right? And then if the second one succeeds, and we're gonna print that out. Probably make sure we unwrap this as well, because it's gonna return as a result, right? Okay. All right, so there you go. Let's see what happens. We don't need these two right now, since we're gonna print right here inside of select. So what this is gonna do, it's gonna race to see whichever one's finished first, and it's only gonna execute on the function that finished first. So the first one, or whichever one doesn't finish, or the slower one, is not going to get executed at all. So let's try that. Run. Okay, so as you can see, everything worked perfectly. It was beating, and then it found Google first. Obviously, we knew that was going to happen. It took 197 milliseconds, and then the overall execution took 202 milliseconds. So instead of join, Tokyo join, which allow us to run both of the futures, we did the select, which makes it basically race to see whichever one finishes first. Alright guys, so now let's talk about channels in task and how we can use this channel to pass messages back and forth between tasks asynchronously. Now, I do have a separate video talking about channels and threads, and that's a whole different topic. That's going to send messages back and forth between threads. This one is between tasks only, and we're going to use the Tokyo runtime in order to execute this operation. So first of all, let's go ahead and comment all this out. We don't need that anymore. And then we're going to start a brand new function called send messages, and it's going to take in a sender, and it's going to be a Tokyo sync MPSC, multiple producer, single consumer sender. And we're going to specify that it's going to be a string that we're passing back and forth here. And the same thing it's going to be for receive messages. Receiver is going to be a Tokyo sync MPSC receiver string. Okay, so we got these two functions. The first one, we're going to have a mutable num string, and we're going to set it to be 1, and it's going to be an integer. We're just going to increment that, and we're going to loop through it, right? And if the num string is equal to 6, so we're going to set it to 6, and that's when we're going to break. Otherwise, it's going to send messages. So we're going to say sender.send, and let's do format. We're going to format a string here, sending message from async, and alright, just like that. And we're going to make sure to await it because it's going to return a future, and also unwrap it in case if there's any errors. Okay, and then after that, we're going to increment the num string by 1. That way we loop from 1 to 6, and we're going to stop at 6. We're going to keep sending messages, and let's try to catch it here on the receiving channel. So we're going to say while let some message msg equal receiver dot receive, and we'll make sure to await that as well because it is asynchronous. Yeah, wait, receiver dot receive dot await. What's going on here? Expecting a block while let some equal. Actually, let's go ahead and put a sleep on this. So we're gonna sleep for, and keep in mind once again, this is the sleep from the Tokyo, not from the thread. Because if we use the sleep method from the std thread here, we're gonna sleep the entire thread. So that's gonna be, it's gonna block the entire process. So for this one, we're gonna use the sleep from that we imported from the Tokyo function. Okay, so we're gonna sleep for a duration of, let's do from seconds. So we're gonna sleep for 1 second. I gotta unwrap that. Okay, so that's good. We'll make sure to await it too, so that we can forfeit the control back to the runtime, so that it can do whatever other the runtime can manage and have other function running if it needs to while we're waiting for it to sleep and waiting for it to wake back up, pretty much. So let's get back to this here. The receiver, mutable. Okay, so mutable receiver. Okay, so we're gonna say, we're just gonna print out the message. Say received, and print out the message. Okay, and that's it. That's it for these two functions. And now we're gonna go to the main function, and once again we need the Tokyo attribute here just to make sure that we are allowed to use main as an async function, so that we can call asynchronous functions inside of main here. Okay, so we're gonna do, let's see, we're gonna return a tuple of sender and receiver, right? And we're gonna go Tokyo sync MPSC channel, And for this function, it does ask us to input a bound number. So a bound number is just however many messages we're allowed to keep inside of the buffer, and we can't spill over. So basically, if we put 5, then we're only allowed to send 5 messages at a time inside of the buffer until it gets read, until it gets received here by the received message. But until the received messages start to receive some of these messages, the buffer is going to stay at 5, for example. But we're going to say 6, right? Because there's 6 messages that we know we're going to send, and then we also got to specify that it's going to pass in strings, a type string. Okay. All right. So then now we're just going to call it, right? So let's see. Let's go ahead and review. Okay. What do you think is going to happen if I just call send messages here, and I'm going to pass in the sender. Await, right? And also receive messages, and I'm going to pass in the receiver dot await. So the receiver is going to have to be mutable. Okay, so what's going on? Oh, it does not need to be mutable. Okay, so what do you think is going to happen now if I run this program? So actually, in order to see better what's going on, we're gonna say let's start time equal instant now, all right? And then at the end, we're gonna say let duration equal start dot elapsed dot as milliseconds. Okay, so we're gonna print that out and say took however many milliseconds to finish receiving. Okay, it's going to be duration, and then also we're going to do a quick print starting receiving channel here. Okay, and we'll do the same thing for the send messages, just so we can see exactly what's happening under the hood. And then start time. Okay, starting sender channel to finish sender. Okay, so what do you think is going to happen if I run this code now? You should know the answer from the first example that we did. It's gonna have to send every single messages, right? And then the receive message will finally start up. So go run. So we started the sender channel, as we can see here. And notice how it started all the sender channel and it finished sending, and then it was able to start the receiving channel. So it's not asynchronous at all. Nothing happened asynchronously in this entire program. Even though we named the function as asynchronous function, we place await at the right time at all these places to let the program knows that, hey, give up control, you know, just go do something else while you wait for this operation to finish. However, like I said, because there was no Tokyo runtime, there was no manager watching over them, they have no idea that there are other operations that needs to be done. So it just happened basically synchronously, right? It just happened as if you wrote this code normally. Now, what do you think will happen if I change this to, let's say, only 1? So the buffer can only carry 1 at a time, 1 message at a time, until it's able to be received and taken out of the queue. What do you think is going to happen now? Nothing. It's going to get stuck. It's not going to finish because it'll start the sender channel, right? And then it'll send 1 message, and the buffer can only hold 1 message, and it doesn't know to give up control to the receiver, so it just sits there, right? So as you can see, it's just sitting here, and it's not going to finish. It's just going to be stuck, and we're just stuck in perpetuity forever. So let's go ahead and exit out. So that's just to demonstrate that, once again, we need a Tokyo runtime in order for us to be able to operate asynchronously. So let's do that now. We're going to say Tokyo, right, join. And we're going to say the same thing as before, send messages, pass in the sender, and then receive messages, pass in the receiver, and that's it. Okay, so now what do you think is going to happen? Now keep in mind, I'm keeping the buffer, the bound buffer, to be at 1. So it's still going to only be able to send one message at a time until it gets taken out of the queue. But as you can see, the code is going to jump from sending message straight to receiving message. So the sender is going to start up, then the receiver is going to start up right away. So let's run that. As you can see, the messages are coming in. We started the sender channel got started, and then the receiver channel got started, and we were able to finish sending every single message, even though we only had a bound buffer of 1. So I mean, and it doesn't change. If we put this to be 5, 6, 7, it doesn't matter. Because of asynchronous operations, we were able to use Tokyo as a runtime to manage and able to switch back and forth between these two concurrently. Alright guys, so for our final example, let's take a look at how an asynchronous program is advantageous to a synchronous one. So what makes the difference, what is the benefit, and I think with this example we're going to get to see that really in good details here. So I already wrote this small program. I didn't want to write it line by line live. It was going to take too much time, so I already finished it. And basically what this does is it writes a sample file, and it loops through from 0 to 10,000, and it writes each individual integer into a sample file called sample.txt, right? And then after that, I opened up a channel, and then for the for the sender, the sender is gonna open up that sample file, and for every single number, it's gonna take that number and send it down the channel, and the receiver is gonna catch it and then write that number into a different file called output.txt. So this is the synchronous version of it, and as you can see with the code, for every single loop, I did put the function to sleep for 100 microseconds for the write and the read. It's gonna go to sleep for 100 seconds, and also for the write sample file as well, just to keep it interesting, just to be able to see everything play out. So we're gonna race to see which one is faster, the synchronous version of this program or the asynchronous version. Okay, so let's go ahead and run this now. So we're running the synchronous version here. And as you can see, it's writing the file right now, the sample file, and it finished writing in 6,500 milliseconds. And now it's reading the file. It finished reading the file in 6,300 milliseconds. And then now it's writing a brand new file called output.txt. And it took 6,000 seconds roughly. And as you can expect, the synchronous program finished in about 19,000 milliseconds, which is the combined sum of these three numbers here. And as you can see, this is what happens. The sample file it's just from 0 to 10,000, and then the output file was correctly written from 0 to 10,000 as well. So that was the synchronous version, right? That was a sequential, just line by line, very simple, normal type of code. Okay, so now we're gonna go ahead and comment that out. Let's see, because we also have an asynchronous version that's already written as well. And right here, this is the asynchronous version. So let's go ahead and activate that. Boom. Okay. So go ahead and pause the video and think about it for a second. What do you think is going to happen when I run this asynchronous version? Like, what is the difference in the time performance here? It's the same exact program. As you can see, I called the sample file the same way, right? No difference here. There's a sleep, the same thing, right? There's a sleep for 100 microseconds, and then also go to async refile, and we have an await here for every single time, for every single loop that we go through that we're trying to send down the channel. We're gonna put an await so that the Tokyo runtime knows to manage it and be like, all right, well, you know, since we're waiting, I'm gonna go do something else instead. Okay, and the same thing with the write file. We have an await here at the receiver, right? So that the Tokyo runtime also know to go ahead and concurrently flip back and forth between each of these two individual operations, right? And we call it with Tokyo join, as we already know. That's how we hand over these asynchronous functions to the Tokyo runtime and let it basically be the orchestrator of how the operation is supposed to be managed. Okay, so go ahead and think about what do you think will happen if I run this program now, the asynchronous version compared to this version. So this version finished in about 19,000 milliseconds. Each individual task took about 6,000 milliseconds. So do you think it's going to be faster or slower? So let's go ahead and run this. Running asynchronous version. All right, so it finished writing the sample file in the same amount of time, roughly. And that's to be expected because there was no await at all inside of the write sample file function. Oh, so look at that. So did that surprise you? So basically we finished in the same amount of time as we did with the regular function here. That's weird, right? Async is supposed to be faster. What happens, right? Okay, and then if you take a look, it actually took longer to read the file and almost twice as long to read the file and also to write the file as the synchronous version. So if you look at this, you might think, wait, what's the point of all of this? I mean, it cost the same amount of time. It didn't run any faster. Matter of fact, each individual function was actually slower, like twice as slow. So my point was, yes, this is exactly what was supposed to happen. Asynchronous programming doesn't magically give you a faster runtime. It doesn't magically just, it's not a burst of speed that you can just somehow pull out of thin air. You still have the same amount of core in your CPU and you're not getting any extra performance. Think of it like if it was just me, right? If I need to do my chores and I have 10 chores to do, if I don't have a twin version of me, another human being to help me, and it's just me, even though I'm doing things concurrently, meaning I'm multitasking, I might be cleaning and then I'll go over there and start cooking and I'll go and I'll start vacuuming. I'm still doing the same amount of work. It's just different timing. So that's basically what asynchronous programming is. It doesn't magically give you a faster program. It doesn't magically just makes everything faster. It just basically allowed you to switch off whenever you're waiting for something. So every time that the program was sleeping or whenever it was trying to send or receive, the Tokyo runtime told it to go ahead and switch off and do something else. And that's why each individual function here took longer, because it kept getting switched off to a different function. It kept getting switched off, and that's why it took twice as long. However, as you can see, the whole program finished in the same amount of time. So it wasn't like, oh, you're gonna add these up and then it's 26,000 plus 6,000, that's about 30,000 milliseconds to be done. No, it's still finished in the same amount of time. Like I said, your CPU is your CPU. You didn't magically create more memory out of thin air. You didn't magically create more speed out of thin air. You're still, in the analogy, you're still one person doing multiple chores, multitasking along the way, but you're still gonna finish the chore in the same amount of time as a whole, right? But it's just more efficient if you were doing an operation that, let's say, you're waiting for a web server to send you a response, or you're waiting for an IO bound task to finish. And so instead of just sitting there waiting, you're able to go do something else. But overall, the amount of time it takes for you to do each one of those tasks is still going to be the same. You didn't magically gain any capabilities, any power, or you didn't just magically spawn another twin version of yourself here. You still have only so many cores in your CPU. It's not like you can magically create more cores, and so you're running on more threads and then is able to do extra powerful performance type of enhancement. So that's the whole point of synchronous and asynchronous programming. It's not a magic pill, but it does help a lot when you have operations that are waiting for an IO bound or a network bound type of situation. Of course, threads is a lot more intensive computational wise, so you want to avoid using threads. You can use 100 tasks per thread. However, you don't want to open up like 100 threads, because that's very heavy, and that's when you switch off threads, it's a lot. Like you open it up, you have a new stack, and you have to open a new stack each time, and it's a lot. And also, threads can only run for the max as much as the amount of cores that you have in your CPU. So you can't, let's say you want to run, you only have 4 cores and you want to run 10 threads. I mean, it's going to run on those 4 cores, but then the other 6 threads going to start having to wait their turn, to take over the cores. So it's not a magic pill, and neither is asynchronous. But I think the point of this entire tutorial is to let you know that yes, you're not getting anything faster. There's no magic pill here. You didn't magically write your code to be to be able to run 10 times faster, 2 times faster, or whatever. But you are being a lot more efficient while you're waiting. So let's say if you have a web server and you have people in queue waiting clients basically in queue waiting. You don't want to if the last client in queue have to wait until every single client in front of him, before he can finally get a request response back. I mean, that's not a good user experience. So basically, it allows him to also get his response around the same time as everyone else, but everybody's, it's going to take the same amount of time to get their response, dependent on however memory is in the server or whatever it is on their client side. It's not a magic pill, but it does make things a lot more efficient and better as far as user experience wise. So I hope that helped, guys. And overall, that this is basically what async and await is in Rust. And it took me a long time to understand this concept. And so I hope I did a good job communicating and explaining things to you guys. So as of now, thank you so much and have a wonderful day. Take care of yourself. I'll see you next time.